In the last part of this program, you learned that distribution transformers are used to change primary distribution voltage to secondary voltage, which a customer can use. The value of voltage carried by a distribution line can be affected by changes in customer load demand and electrical characteristics that cause power losses. In order to compensate for these losses, voltage regulators and capacitors are used. In this part of the program, we're going to teach you how to identify voltage regulators and capacitors and give you a basic explanation of how each of these devices does its job. We'll begin with voltage regulators. A voltage regulator is an electrical device that maintains distribution voltage within a specified range of values. This simplified diagram illustrates the basic electrical components found inside of a voltage regulator. They consist of a primary winding, which is wired in series to a secondary winding. The series connection causes the primary winding to also function as part of the secondary winding. A tap changing mechanism connects the voltage regulator to the distribution system through taps. On our simplified diagram, 5 taps are shown. In an actual voltage regulator, there may be 30 or more taps. When voltage is applied to the primary winding, the resulting current flow induces a voltage in the secondary winding. This is similar to the operation of the transformer we looked at earlier. However, unlike transformers, the series connection between the windings causes the primary winding to also function as part of the secondary winding. Depending on which tap that connects the voltage regulator to the distribution system, the value of voltage leaving the regulator may be greater than, less than, or equal to the voltage applied to the primary winding. The voltage supplied to and tapped off voltage regulators is primary distribution voltage. All a regulator does is adjust the voltage within a specified range of values in order to correct for drops in voltage caused by changes in load demand and characteristics of distribution lines. Now that you have a basic understanding of what a voltage regulator does, let's see what one looks like in a distribution system. This simplified diagram illustrates what a typical voltage regulator looks like. The electrical components are contained inside a cylindrical housing that is usually longer than the housing on a typical distribution transformer. On the top of the housing are 3 bushings. This bushing allows the primary lead from the distribution line to connect to the primary winding. This connection is usually designated as line on a regulator. This bushing connects the lead from the tap changing mechanism to the distribution line. This bushing is usually designated as load on the regulator. The voltage regulator is grounded through this 3rd bushing. 2 additional features found on most voltage regulators are a control panel and a tap position indicator. We'll look at these in more detail in just a minute. Here's a voltage regulator installed on a utility pole. Notice the characteristic shape of the housing and the 3 large bushings located on top of the housing. Unregulated primary voltage is applied to the primary winding through this bushing marked line. Regulated primary voltage is supplied to the distribution system through this bushing marked load. The 3rd bushing is connected to ground. A nameplate on the regulator housing provides specific information about the capacity and wiring design of the regulator. Located on the side of the regulator is the tap position indicator. The indicator consists of a faceplate calibrated to show both increases and decreases in voltage. In this example, a primary pointer and 2 memory pointers are also a part of this indicator. The 0 on the faceplate indicates a neutral tap position. This means that the unregulated line voltage and the regulated load voltage are at the same value. The numbers to the right of the 0 indicate the position of the tap changing mechanism when the value of the load voltage is being increased over the value of the line voltage applied to the regulator. The numbers to the left of the 0 indicate the position of the tap changing mechanism when the value of the load voltage is being decreased from the value of the line voltage being applied. This pointer indicates the actual position of the tap changing mechanism at any point in time. The memory pointers on each side of the pointer indicate the highest and lowest tap position reached by the regulator since the last time the regulator was inspected, and the memory pointers were reset. This wire connects the voltage regulator to its control panel, which is located on the pole near the ground. Inside the panel is an analog computer. The computer is programmed to respond to changes in line voltage and cause the regulator to increase or decrease the value of the regulated voltage within a specified range of values. One way of identifying a voltage regulator is the manner in which it fits into the distribution system. A disc or other insulator is usually installed in the distribution line near the regulator. Unregulated voltage is applied to the regulator from a tap on this side of the insulator. A wire runs from the tap through an isolation switch to the line side of the regulator. Regulated voltage is supplied to the distribution system through a wire connected to the load side of the regulator. The wire also runs through the isolation switch to a tap on this side of the insulator. In most cases, each phase wire of a distribution line is attached to a separate voltage regulator. The regulators may be mounted on separate utility poles like these, or in some cases, 3 regulators may be mounted together on a platform. Voltage regulators are an important part of a distribution system because they ensure that a customer will be supplied with electricity at a usable voltage. Voltage regulators and transformers are primarily used to affect the voltage in a distribution system. Capacitors are used to affect power. By multiplying the amount of voltage applied to an AC circuit by the amount of current flowing through the circuit gives you the amount of power in the circuit. Now, power is a complex topic, which you'll learn about in great detail later on in your training. For our purposes right now, you need to understand that there are several different types of power. Some of the power is usable, and some is not. In a distribution system, which is basically an AC circuit, voltage and current constantly rise and fall. Ideally, when voltage and current rise and fall at the same time, usable power is produced. In reality, however, voltage and current often rise and fall at different times. This produces reactive power, which is not usable and reduces the overall efficiency of the system. Reactive power can be a problem in distribution systems because it affects the amount of power that can be supplied to a customer. To compensate for reactive power, capacitors are often used. In this part of the program, we'll give you a basic explanation of how capacitors work and teach you to recognize them. A capacitor is an electrical device that can accept a charge, store it, and release it. The manner in which capacitors charge and discharge increases the efficiency of a distribution system so that more usable power is available for customer use. This simplified diagram illustrates the basic parts of a single-phase capacitor. It consists of 2 plates separated by insulation housed in an oil-filled container. One of the capacitor plates is connected through this bushing to the distribution line. The other plate is connected through this bushing to ground. In an AC circuit, voltage continually increases and decreases. As voltage increases, the capacitor charges. This means that one plate becomes positively charged and the other plate becomes negatively charged. When voltage begins decreasing, the capacitor discharges. The capacitor continues to charge and discharge as the cycle repeats. Capacitors are very easy to recognize because they are square or rectangular in shape. The number of bushings on top of the capacitor may vary. These are three-phase capacitors. In most cases, you'll find capacitors connected together in banks. Here, individual capacitors are connected together to meet the load requirements of a specific service area. The ability of a capacitor to counteract reactive power does a great deal to improve the overall efficiency of a distribution system. A capacitor's ability to store a charge, however, can present a considerable safety hazard to you and other T&D personnel. Capacitors do an excellent job of storing an electrical charge. In fact, they will remain charged even after they are isolated from a system. When working on capacitors, it is extremely important to your safety that you follow your company's procedures for discharging the capacitor before starting any work. This will ensure your safety and the safety of others working with you. In this part of the program, we've shown you what voltage regulators and capacitors look like, and we've explained the job each performs. Voltage regulators keep voltage within a specified range of values. Capacitors improve the overall efficiency of a distribution system by compensating for reactive power. In the next part of this program, we'll begin discussing how distribution systems are laid out and how they are protected.